Definition of derivative. So we already know what a derivative is, and it represents a rate of change. However, specifically, the derivative at a point is the limit of the rate of change. So it's going to be the limit of the average rate of change. When we can't find the instantaneous rate of change, we can only find the average, and then we can estimate the instantaneous rate of change. So using this information, if we wanted to actually find a derivative of f of x at x equals 8, we would start with the average rate of change. Now our average rate of change is going to be f of x minus f at 8. That's the change in our y's divided by the change in our x's, which would be x minus 8. So if I actually want to find the derivative of this, or estimate the instantaneous rate of change, I would need to take the limit of this rate of change. So we want 8 to be one of our x values, and the other x value that we're using in this actual expression that we have for the rate of change needs to be very close to 8, which means we're actually taking the limit of this average rate of change. So we're going to take the limit of this average rate of change as x approaches 8. We want to get really, really close to 8. So to write that limit, we would have the limit as x approaches 8 of our average rate of change. And this is mathematically how we say, well, we're going to plug in values closer and closer and closer to 8. So the notation to represent the derivative of a function is we write f at the little prime after it of x. That means the derivative of f at x. The notation for the derivative of f of x at x equals 8 would then be f prime parentheses 8. That means the derivative of the function f at the x value 8. So now we're going to write a equation for the limit that we have written in red above. And all I'm going to say now is, well, the derivative, at 8, the derivative at 8 will be equal to this rate of change, will equal to this limit as x approaches 8 of our rate of change. Sorry about that. So that's how we'd write the equation for f prime of 8, or the derivative of 8. So the definition of derivative that we're going to look at in just a minute allows us to write the equation to find the derivative of a function at any x value called c. In our case, our c was 8 in the one we just did, but this will work for any value that we want. Now, this definition that we're going to write down, you must know this for the rest of your calculus life. As long as you are in a calculus class, you have to know this. So the definition is f prime at c, so any x value that we're calling c, is going to be the limit as x approaches that c value of f of x minus f of c all over x minus c. And that will work for any value. The one we had written above was only good at x equals 8. This definition is good at any x value we want. This means that the instantaneous rate of change of f of x with respect to x is at x equals c, and it also means the slope of the tangent line to the graph at x equals c. And again, memorize the definition that I have in green. So let's do this first example. We have a function, and we are asked to use the definition of derivative to find f prime at 5, and then we also are asked to actually write the equation of the line tangent to f of x at x equals 5. And if I want to write the line tangent to the graph, I first need the slope of that line, which the derivative is going to give me. So first identify what it is we're finding. In this case, it is f prime of 5. And then we're going to do the limit as x approaches that value, which is 5. And we're just going to do f of x, the change in y's, minus f of 5, over the change in x's, x minus 5. And when I work that out and plug in my f, that's the limit as x approaches 5 of x cubed minus 3x minus 4 minus what I get when I plug in 5, which is 5 squared minus 3 times 5 minus 4, all over change in x, which is x minus 5. And then I need to work this out. Now, we've done our calculus. All we're doing right now is arithmetic and algebra. My x cubed minus 3x minus 4 stays the same. I work out what I have here. I have 25 minus 15 minus 4, which I believe is 6, all over x minus 5. And then what I can do is just combine my like terms and rewrite this again. Anytime I rewrite it, this limit as x approaches 5 must be there because this isn't an equation without an actual limit value there. So we end up with x cubed minus 3x minus 10 over x minus 5. Now, right now I still cannot plug in x equals 5. I get a 0 in the denominator. So I need to do some factoring on the top to see if I can simplify this fraction. And when I factor the top, I get x minus 5 times x plus 2. And my denominator is x minus 5. At which point I do end up with this thing in the box, which is a silly version of the number 1 that can be simplified out. So all I really have is the limit as x approaches 5 of x plus 2, at which point I can simply plug in my 5. I don't have any problems with doing that. And this limit is equal to 7. I'm going to go ahead and rewrite that. F prime of 5 is equal to 7. So that's the first part of what this example was asking me to do. The second part was saying, okay, great, now write the equation of the tangent line. So if f prime of 5 is 7, if my derivative is 7, that tells me that my slope of my tangent line is going to be 7. So I've got my slope. The other thing that I need is I need a point. Well, I wasn't actually given a point. I was given an x value. So my point's going to be at x is equal to 5. So I can find my y value by plugging 5 in, and I get 5 squared minus 3 times 5 minus 4, which we actually calculated above, and I believe we got that to be 6. So I actually do have a point. Even though I wasn't actually given an entire point, if x is 5, I know that I can find what my y value is, which is 6. Now, I would like for you to always use point slope. And when you use point slope, don't simplify anything. I don't want you to make any mistakes. Point slope is fabulous. So I have y minus y1 is equal to m times x minus x1. That's your point slope formula. That's the line equation that I would like for you to use. So we have y minus y1, in this case was 6, equals m, which was the slope of our tangent line, 7, times x minus our x value, which was 5. I want you to leave it like this. Less chance for error. You can, if you want, put it in y equals mx plus b form, which is y equals 7x minus 29, but there's no need to do that. So, moving on. We actually have another definition of derivative, and this is another one that you do need to memorize. Now, this is a definition of the derivative as a function. Before, we actually got a number. We were finding the derivative at a specific x value. This one is not going to be a number. It's actually going to be a function. So that's the difference between the one we just did and the one we're doing now. What we need to recognize is what we're doing is actually we're finding the limit as our change in x is getting smaller and smaller and smaller of the change in y over the change in x. That's all we're really doing here. So to write that in terms of f, we have f prime of x, which is going to be a function, is going to be the limit as our change in x approaches 0 of our change in y. Well, our change in x is delta x, so I'm going to start with the bigger value, and that's going to be f of x plus my change in x. My change of x could be 0.1, 0.2, 0.3, whatever that change of x is going to be, I'm going to add it to x. I'm going to subtract out whatever f of x is, and I'm going to divide by whatever that change of x is. Now, mathematicians are lazy, so we don't always like to write delta x. So sometimes what we do is we write that the derivative is going to be the limit as h approaches 0. H is in place of the delta x. So we have f of x plus h minus f of x all over h. So this is the one that we will typically use, but it is exactly the same as the one with the delta x. If you like delta x, please use delta x, and if you are lazy, then use the h. So this is the instantaneous rate of change of x with respect to x. And this will also give you the slope of the tangent line of the graph. However, you will have to provide the x value that you want if you need to get a number. So moving on to example 2. We have f of x is x cubed. We're going to use the definition of derivative to find an equation for f prime of x, so not a number. Then I'm going to use that equation to find f prime at 7. That will be a number. So for our example 2, we're trying to find f prime of x, and that's going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. And now I'm going to plug that in. So that will be the limit, again, as h approaches 0, of, I'm plugging x plus h into my function, so that gives me x plus h cubed, minus, I'm plugging x into my function, that just gives me x cubed all over h. Now we get into some algebra. I know what x plus h raised to the third power is. If you don't, you want to pause the video here and work that out and see what you get. My expectation is that you will be able to do this on an assessment by using the definition of derivative, so working this out. So go ahead and pause it if you need to do the algebra. So we end up with the limit as h approaches 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed. That's my function when I plug in x plus h. Now I still need to subtract the x cubed. That's still on the top of my fraction, and I'm still over h. Now we're just going to do some combining like terms if we can. And what I notice is that I have an x cubed in the front. I have an x cubed that's negative in the back. So x cubed minus x cubed is 0. So on the top, what I really now have is 3x squared h plus 3xh squared plus h cubed all over h. And from here, when I try and plug in 0, I have a 0 in the denominator. If I could simplify that h in the denominator with an h in the top, my life would be easy. So what I actually need to do is look at the top, and I can factor an h out of the top. So I'm going to do that. The limit as h approaches 0. Factor out my h. I'm left with 3x squared plus 3xh plus h squared all over h. That makes me happy because this right here is a silly version of the number 1, and I don't need to keep writing it down. So now I have the limit as h approaches 0 of 3x squared plus 3xh plus h squared. At this point, I can simply plug in h as 0. That gives me 3x squared plus 0 plus 0, and that just leaves me with 3x squared. So this is the function to represent the derivative. So f prime of x is going to be 3x squared. The next thing I was actually asked to find is I want to find f prime at 7. So to find f prime at 7, I'm simply going to replace the x with a 7. And this ends up being 147. So f prime at 7, the derivative at 7 is 147, or the slope when x equals 7 is 147. Which is why this is so much more useful to get an actual equation of the derivative so that I can use it for any x value I want. Now, we've just sort of discovered a cute little rule called the power rule. So what we had, just to kind of recap, we had f of x was x cubed. When we found our derivative, it ended up being 3x squared. So let's talk about where these things came from. The 3 that was the exponent, that comes out front and becomes the constant. What is now the exponent of the derivative is the old exponent minus 1. So if you look in the box where it says derivative of the power function, that's a mathematical way to state what we just did. If I have something raised to a power, the derivative is going to be that power times x raised to 1 less than the power. However, the exponent has to be a constant. This does not work if I have 2 raised to the x, because x is a variable and I cannot have the exponent being variable. It must be constant. So let's go through example 3. And all we're going to do here is take each derivative. Now, with the first term, we have this 5 out front. My derivative is going to be that same 5 times the derivative of my x to the 7th. So the derivative of x to the 7th, my exponent comes down in front. My x is now raised to 1 less, which is to the 6th. For the next term, again, my constant stays, and I'm going to multiply by the derivative of that term, which my 3 comes down. X is now raised to 1 less, which is 2. Moving on, I have 12 times my derivative. The exponent on x is simply a 1, so I have 1. X is now raised to 1 less, which is 0. And lastly, I have minus 47 times, well, if I have no x's, then I have x raised to the 0 power, which means when I take the derivative of this one, I have 0 times x raised to the negative 1. But 0 times anything is 0. So let's rewrite this now. I have 35 x to the 6th minus 33x squared plus 12 minus 0. And I don't need to write that minus 0, so we would typically just leave it like this. And that's the function for our derivative. So key piece of information about a constant. 47 was our constant. And when we found that derivative was 0. So the derivative of a constant is 0. If you think about it graphically, when you have a graph of a constant, if you were to look at the slope of that, if I've got an axis and I graph my constant, whatever that is, the slope of that line is 0. So my tangent line would be the exact same line, and the slope of that line would be 0. So every constant's derivative is 0. Terminology. This is all the different ways that we can talk about derivatives. So if we have y equals f of x, we can represent the derivative these 4 different ways. The first one we've already talked about, and we would say that as f prime of x. The next one, we could also be lazy and just call it y prime. That's also the derivative as long as we have a y involved. If you just have a function written as f of x equals something, you can't call it y prime. It's only if you have y equals something. The third way is spoken when you say it, dy dx, and that means the derivative of y, and the over the change in x, so the change in y over the change in x, which is your rate of change. And the last way is saying d dx of y. The key to that one is this is an operation. It tells you take the derivative of y, as opposed to the others which say the derivative is something. Hope you enjoy the rest of your day.